Hello and welcome to SigmaXL video tutorials. In this video, I'll be covering basic Taguchi Design of Experiments templates, which are new in SigmaXL. Dr. Genichi Taguchi was a Japanese engineer and quality consultant who codified his consulting techniques into a formal methodology. This generic engineering tool, called the Taguchi method, is used for system studies. The purpose of these studies is to reduce system variability while simultaneously decreasing costs and increasing productivity. The features of the Taguchi method include extensive use of experimental design, separation of factors by role, control, and noise, use of measures of variability as responses, dual objectives of process centering and noise minimization, and use of loss functions for economic justification of each application. The Taguchi DOE templates are similar to the other SigmaXL templates. You simply enter the inputs and resulting outputs are produced immediately. To open the templates, click SigmaXL, Design of Experiments, Basic Taguchi DOE Templates, or SigmaXL, Templates and Calculators, Basic Taguchi DOE Templates. Included are Taguchi L4 2-level, 2-factor with two-way interaction, or 3-factor, Taguchi L8 2-level, 3-factor with two-way interactions, 4 to 6-factor with alias two-way interactions, or 7-factor. Taguchi L9, 3-level, 2-factor with two-way interaction and 4-factor. Taguchi L12, 2-level, 11-factor. Taguchi L16, 2-level, 5-factor with two-way interactions, 8 to 14-factor with alias two-way interactions, and 15-factor. Taguchi L18, mixed 2 and 3 level, 3-factor with two-way interactions and 8-factor with AB interaction. And finally, Taguchi L27, 3-level, 3-factor with two-way interactions and 13-factor. Each template features discrete categorical levels, so they may be numeric or text-based. These templates are also fill-in-the-blanks templates, so charts automatically update. They include a predicted response calculator and charts for mean, standard deviation, and signal-to-noise ratio. The available signal-to-noise ratios are nominal is best with variance only, nominal is best mean squared deviation with target, larger is better, or smaller is better. They support up to 27 replications for the outer array. They also provide Pareto of deltas or effects, and ANOVA sum of squares % contribution for main effects and two-way interactions, main effects plots and, if applicable, interaction plots. And for designs with aliased interactions, a drop-down list of available aliased interactions is provided. This is much easier to use than linear graphs. Column assignments to orthogonal array are optimized to ensure maximum design resolution. To demonstrate, we will begin with the Taguchi L8 2-level 3-factor robust cake example. This is the same robust cake experiment adapted from the video Designing Industrial Experiments, which was actually used in the SigmaXL workbook using a 3-factor full factorial model. Here we will use the Taguchi L8 3-factor. An example of a completed template can be found within SigmaXL. To access the template, click SigmaXL, Help, Template Examples, Taguchi Examples, L8 3-factor robust cake. If you wish to start with a blank template and populate the values like we will be doing in this video, click SigmaXL, Design of Experiments, Basic Taguchi DOE Templates, Taguchi L8 2-level, 3-factor with two-way interactions. The response is taste score on a scale of 1 to 7, where 1 is awful and 7 is delicious. The goal is to maximize the taste score with minimum variation, so we will maximize the signal-to-noise ratio, SN larger is better, selected from the list. The inner array controllable factors are egg, butter, and flour. Actual low and high settings are not given in the video, so we will use coded 1 and 2 values for level 1 and level 2. We are looking for a combination of egg, butter, and flour that will not only taste good, but consistently taste good over a wide range of cooking time and temperature conditions. The runs were randomized and order recorded in the column run number. The outer array taste score values are entered as shown. These 5 outer array values to be used have different cooking times and temperature conditions. Scroll to the right to view the calculated statistics. We will focus our analysis on the signal-to-noise ratio and review the mean and standard deviation afterward as a check on the results. Scroll right and down to view the Pareto of deltas for SN ratios. Delta is the difference between the maximum and minimum average response for the levels of each factor in the inner array. It appears that egg is the dominant factor followed by butter. Scroll down to look at the main effects plot for SN ratios. Let's adjust the y-axis to get a better scale. Right-click on the y-axis and select Format Axis. In Axis Options, set minimum to 8 and maximum to 14. It initially appears that the maximum taste score occurs with egg equals 2, butter equals 2, and flour equals 2. This design permits the analysis of interactions, so we will look at the Pareto of ANOVA SS, or sum of squares percent, contribution for SN ratios, which includes the main effects and interactions. Now we see that the egg-butter interaction is clearly the dominant factor, which is in agreement with the analysis done using the 3-factor full factorial in the SigmaXL workbook. The error term in this model is the 3-way interaction, which is assumed to be negligible, so is not included in the model. Scroll down to view the interaction plot for SN ratios for the egg-butter interaction. I'll adjust the y-axis for better visibility. We can clearly see the large effect due to the 2-way interaction. The effect that egg has on taste depends on what the butter setting is. The maximum signal-to-noise ratio for taste score is achieved with egg equals 2 and butter equals 1. Also, if desired, the interaction plot x-axis legend factors may be switched by clicking on the chart, then selecting Excel, Design, switch row column as shown. From the previous plots, we conclude that the optimum setting to produce a maximum taste score SN ratio is egg equals 2, butter equals 1, and flour equals 2. If we only considered the main effects plot, we would have incorrectly set butter equals 2. Scroll up and left to view the predicted output calculator. Enter these values. Factor settings can be manually entered or selected from the drop-down list, as I'm doing here. This gives the predicted mean, standard deviation, and signal-to-noise ratios for taste score. The calculator treats the factors as categorical, so levels can be numeric or text. The drop-down list is a convenient way to select the factor levels, but unfortunately, Excel Solver can't be used with this calculator to perform optimization. Please refer to the workbook to see how to use the solver with multiple regression. As a validation of our signal-to-noise ratio analysis, we will review the plots for mean and standard deviation. From the Pareto of ANOVA sum of squares percent contribution for means, we see that the egg-butter interaction is the dominant contributor to the mean taste score. Looking at the egg-butter interaction plot for means, the optimum setting to maximize mean taste score is egg equals 2 and butter equals 1. Looking at the Pareto of ANOVA SS percent contribution for standard deviations, flour is the dominant factor for standard deviation. The main effects plot for standard devs shows that the optimum setting to minimize the standard dev taste score is flour equals 2. This is in agreement with the settings determined from the signal-to-noise ratio. Taguchi advocates the use of signal-to-noise ratio as it is simpler by looking at only one variable, but some practitioners prefer to analyze the mean and standard deviation separately. This concludes part 1 of the SigmaXL Introduction to Taguchi Templates tutorial video. For more videos, visit us at www.sigmaxl.com or join us at our YouTube page. Thank you for watching.